First two parts of the homework were a sketch showing a muscle. Within a muscle, a bundle of muscle fibers, and a muscle fiber is a muscle cell. Within each cell in a skeletal muscle, there's a myofibril with a row of sarcomeres. So this is one cell here, and it would go on here. Within it is a row of sarcomeres. If we zoom in on a sarcomere, number 2, we see the ends of the sarcomere, those proteins, the strands of actin here attached to the ends, some spacers, not so critical for us, titin, and then the myosin heads on bundles of myosin oriented at different directions at the two ends. So here's the myosin heads, and they can bind to and interact with the actins. Tropomyosin is wrapped around the actins in skeletal muscle. So here's a tropomyosin, and here is troponin, the calcium binding protein. Calcium binds, and these would be pulled away. The cycle of myosin contraction. So we start off in the cocked position with an ADP, and a phosphate, held in binding pockets, not covalently bound, just held in binding pockets. Upon binding, that binding pocket for the phosphate opens up, and the phosphate pops free. Losing that -2 charge violently causes here's the phosphate popping free. It violently causes the myosin head to change shape, and so it shifts into the rigor position, still attached to the actin. So here we are shifted, and once that has happened, then the ADP can leave. We're stuck in the rigor position, still bound, until we get a new ATP coming in and binding. Once that ATP is bound, it can split, hydrolyze, in other words, into an ADP and a phosphate, which in the process shifts it to the cocked position, and we start over. There were other ways to sketch it, and here's another example showing the start here, ADP and phosphate, and it's bound. Upon binding, that releases the phosphate. Myosin head is now unstable in that conformation, and so it shifts. That's shown here, whereupon in the new conformation, ADP is not held in that binding pocket well, so ADP is released, but we're still locked in the rigor position until we get a new ATP in. Until we get a new ATP in, that ATP binding then allows it to detach. So here it shows it detached. ATP is then converted into ADP and a phosphate, and it goes back to the cocked position with ADP and phosphate, and we can start over. Events of an action potential to control a skeletal muscle. We have an action potential coming down. This voltage-gated calcium channel would open. Calcium binds to a calcium binding protein. That releases neurotransmitter. At a muscle, it is acetylcholine. It's the neurotransmitter. And that binds to acetylcholine receptors, which are ionotropic receptors. So the receptor is a channel. Here's the sodium coming in. The AP spreads along the membrane. This is the T-tubule, and the membrane is spreading down along the T-tubule. Wherever it gets close to sarcoplasmic reticulum, which has calcium stores, the calcium is pumped in. It's an ATP ACE. So calcium is pumped in. We get calcium building up inside. A voltage-gated calcium channel. This is a voltage-gated calcium channel here. Responds to that voltage and allows calcium out. There are calcium activated channels in some as well. and so you get a wave of calcium escaping. That calcium binds to troponin. That exposes the binding sites. Here's the tropomyosin pulled off. Here are the binding sites for myosin. That allows contraction, and upon contraction, we start off with the myosin heads at the ends here, but as we have repeated cycles of contraction, the ends of the sarcomere get shorter. What if you had a mutation in the myosin gene that caused the protein to bind with higher affinity to phosphate? How would that change muscle contraction? So, multiple possible answers. Here's one. The phosphate, shown in a sketch, the phosphate stays. So even though it's bound, we are slower to release that phosphate. And so because we're slower to release that phosphate, this should be ADP. So it's going to slow everything down, and it's going to be slower until we release the ADP here. In words, the muscle contraction would be slower because phosphate needs to leave to change from the cock to the rigor position. Here's a different prediction. Here we have the myosin head, got an ADP here and a phosphate here. It pops free, but that's the normal one. It normally pops free, causing the myosin head to change position from the cock to the rigor position, but with higher affinity, that phosphate does not escape. And so if it's not escaping, we'd get low contraction, much harder to move limbs. Number 6, what if we had mutation in troponin, so it binds with lower affinity? In other words, here's our calcium. It is going to escape more quickly. It's got lower affinity, less strength of attraction. So in words, muscle contraction would be shorter because if the calcium doesn't stay, it may not fully contract because the calcium doesn't hold on to the calcium. Tropomyosin is not pulled away. So you're going to get briefer and less contraction. So another interpretation, because the calcium is leaving more easily, you're going to have a faster recovery after contraction, and that would also be true. And here's another one. So normally the calcium would bind tightly enough to pull this away, but now the calcium with low affinity, it is not staying, so that it is harder to even begin contraction because the calcium keeps binding and popping free again. So it pops off and doesn't move the tropomyosin off of the actin. And the last one was just to make sure you could still do these things from an earlier one, and some people sketched it and some just said they could.